A very good day to all the participants. Today we are going to discuss about the boiler and power station water treatment and wastewater management. Basically, in the power plant, several types of water requirement is there, and we have different treatment procedure, and these pre-treatment and post-treatment procedures will be discussed today. The main objective of the water treatment and maintaining water chemistry in thermal power stations may be from the perspective of ensuring long-term integrity of the materials of construction of the tubes and other water flowing parts, steam flowing parts, and to the system, and to maintain the quality of steam for the purpose of use. The type of treatment varies on type of material, operating conditions, system design, and definitely bad water chemistry leads to internal deposits or metal wastage and various other metallurgical damage, like your tube failure due to hydrogen damage or caustic embrittlement or stress corrosion cracking, short term and long term overheating of tubes, and that is caused by internal deposits. So all these failures may observed. Raw water contains impurities which must be removed for quality steam generation. The source of this may be natural or man-made, and these impurities has to be assessed by sampling, and typical terms that we use for this water analysis result display, there are certain units of measurements like ppm, parts per million, measure of proportion by weight, ppb, parts per billion, measure of proportion by weight, milligram per liter, it is measure of weight by volume, and 1000 ppb equal to 1 ppm. When specific gravity of liquid is 1, then 1 ppm equal to 1 milligram per liter. pH is the measure of alkaline or acidic nature of a solution. It is actually negative logarithm of hydrogen ion concentration in a solution. For acid, pH ranges from 0 to 7. At 7, pH is neutral. Alkaline range pH is from 7 to 14. Regarding conductivity, it is the measure of the ability of a solution to carry an electrical current. Current is carried by ions, and both positively and negatively charged particles carry current, but at a different degree. Conductivity gives an estimate to the dissolved solid concentration, and it is measured with respect to certain value multiplied by specific conductivity. Unionized weak acid or bases and uncharged soluble organic matter that is not carrying any current, and that cannot be measured by conductivity. Cation conductivity of a solution where all cations have been replaced by hydrogen ion by passing through an ion exchanger column, that is called cation conductivity, and this conductivity of hydrogen ion is 4-5 times the conductivity of any light material like sodium, potassium, calcium or magnesium, and cation conductivity will be greater than the specific conductivity of most of the raw water samples. Now, to understand the total dissolved solids or suspended solids, the solid particle may be dissolved in a water supply or in an ionized form or unionized particle, or it may be simply be suspended as a particle of the water supply. Suspended particles are unionized and do not carry a current and cannot be measured by conductivity, but suspended particles may often be measured by another term which is called turbidity, which can be by filtering a sample and weighing the dried filter we can measure it. And dissolved solids may be ionized or unionized. But if the dissolved solids are ionized, they will carry a current, and therefore we can measure it by conductivity. Dissolved solid cannot be filtered from the solution because it is dissolved within it. Hardness is a result of metallic cations like calcium, iron, magnesium, manganese, and their carbonates and sulfates. They form the hardness. By hardness we mean how the water is made difficult to form a leather with soap and produce scale in a hot pipe or tube. Let us try to understand some more terminologies used in water sampling and analysis. Like raw water, it is the water received from various sources. Treated water, water which has undergone any treatment and to make it suitable for any industrial or other purposes. Softened water means water which has the hardness suitably reduced and removed. Demineralized water means water without dissolved salts which are removed significantly to very low concentration by passing through a ion exchange mechanism or not by distillation. Some more terminologies. Condensate is the steam condensed which is unmixed with any other water, and steam which has been condensed back to water through the process, and it is reusable in steam production. Boiler feed water is the stored water in feed water tank at BFP inlet. Any mixture of different source of water in feed water storage tank, that can be called as boiler feed water. Makeup water means any cooling water system, or defined as the amount of water added to the system to balance the losses due to blowdown or leakages and drainage and other evaporation losses. Makeup water actually equal to blowdown losses and evaporation losses and drainage losses. Blowdown water is actually drained continuously or intermittently from boiler drum or cooling water system other than evaporation, and this is actually to maintain the level of impurity within the control of the total process. In thermal power station, feed water system is made up of different parts like deaerator, boiler feed pump, piping from deaerator to boiler, then feed water supply system within the boiler, then steam passages are there. Steam, water passage also includes the economizer, then downcomers, then you have water walls where water steam circuit part is there, then we have superheater and reheaters. So these are all parts, and there is a makeup water also and condenser also, which constitute part of feed water. The makeup and condensate mixed ahead of deaerator and passes through the deaeration system, then goes to the storage tank, boiler feed tank, from where water is fed into the boiler feed pump, and there may be booster pump, and from BFP discharge through HP heaters it is going to the boiler again, and water is having the highest specific heat than any of the common inorganic substance, and steam is capable of carrying large quantity of heat. As you know, the specific heat capacity of steam is very high. That's why these unique properties are utilized as for power generating process, and in steam cycle, Rankine cycle based power generating process. The amount of minerals that can be dissolved in water varies from 30 gram per liter in seawater to anything around 1500 milligram per liter to 0.005 milligram per liter in freshwater supply. Then water impurities basically cause boiler steam generation quality as well as the common impurities in the raw water can be classified as shown in the chart. Dissolved solids are substances that will be dissolved in the water like carbonates and sulfates of calcium and magnesium. These are scale forming substances when heated. Then there are other dissolved solids which are non-scale forming. That's why we require softening, dealkalizer or demineralizer arrangement to remove these dissolved solids. Now suspended solids are substances that exist in water as suspended particle. They are usually mineral or organic in origin. These substances are not generally a problem as they cannot be filtered out. So that's why we have pretreatment facilities like filtration, settling and clarification to remove these suspended solids. Now dissolved gases like oxygen and carbon dioxide can be readily dissolved in water, and they has to be removed because oxygen may come from leakage air within the condenser. So these gases are instigator of corrosion. So naturally we have to remove them, and that's why deaerator and activated carbon filters are used to remove these gases. Now the purity requirement of any feedwater system depend on how much feedwater is used as well as what the particular boiler design is providing in terms of pressure, heat transfer rate and temperature at which the boiler is operating. And naturally you have to see that purity is maintained according to the desired OEM reference. If the feedwater does not meet these requirements, we must pre-treat the water to remove the impurities. There are three main reasons of water treatment. First one is definitely prevention of corrosion of material in boiler feedwater, steam and condensate flow system, and elimination of formation of internal scale and economic boiler operation without carryover of any solids with steam like silica. Common feedwater contamination is forming the boiler deposits. Most deposits can be classified in one or two types. Scale that is crystallized directly onto the tube surfaces, and sludge deposits that precipitated elsewhere and they are then transported to the metal surface by the flowing water and then gets deposited. Deposits typically found in boiler that includes calcium and magnesium salts like carbonates, phosphates and sulfates. There may be silica deposit, iron oxides. Now carbonate deposit is usually granular and sometimes very porous in nature, and sulfate deposit is much harder and dense than carbonate deposit because the crystals are smaller and cement together tighter, but they are more brittle. Now silica deposit is very hard, resembling like porcelain, and crystals of silica extremely small, forming a very dense and impervious scale sometimes found in tube surfaces. And these scales are extremely brittle and hard and very difficult to remove. Iron deposits are sometimes found, which is resulting either due to corrosion or contamination of water, and they are dark colored and found very well within the subsurface. Now sludge is the accumulation of solids that precipitate or enter the boiler as suspended solids, and the sludge deposits can be very hard and dense, and when exposed to high heat level they often just like baked in the place and become hardened, and it may be a very hard scale, and once deposition starts, these sludge particles present in the water can become bound to the deposit again and becoming larger and larger. So we find depositions causes low boiler efficiency by acting as an heat insulator and restrict boiler water circulation and increase the drag coefficient in the circuit, reduces the circulation in tube and that contributes to accelerated deposit. Sometimes overheating and premature tube failure can be seen. Steam water separation may be advanced and corrosion of the tube metal surface and increased boiler cleaning requirement may be resulted from these deposits. Let us try to find out the other issue, that is corrosion. Corrosion is the loss of metal as it oxidizes back to the ore form, like iron reverts to iron oxide. Corrosion can be uniform over metal surface or localized, resulting in deep pits in the metal. Pitting corrosion caused mainly by the dissolved oxygen and can result in tube failure. Corrosion, generally different types of corrosions are there. Mostly predominants are galvanic corrosion, caustic and alkaline corrosion, hydrogen embrittlement and oxygen pitting. The third major problem related to boiler operations is carryover into the superheated steam. The steam from boiler should always be dry and should have minimal dissolved solids, but carryover may be due to mechanical effect or may be caused by the volatility of certain dissolved salts like silica and sodium compounds, or it may be caused by foaming in the boiler drum. Boiler water carryover results poor quality of steam and caused by two problem areas, which are called foaming and priming. By foaming we mean that when bubbles form on the boiler water surface and live with the steam, that is called foaming. Foaming is caused by high TDS and high suspended solid and contaminants such as oil, grease, fats and certain organic compounds available within the feed water which is coming up to the drum. Oil in particular can cause major problems due to the saponification process, where it reacts with the caustic in the boiler water and forms soap-like compounds. Now priming, priming it is a more severe form of carryover when there is a sudden surge of boiler water level and boiler water is drawn into the steam line, superheated steam line, and as a result it is caused by operating condition in the boiler above its rated condition, and these sudden changes in steam demands or finally by the operating water level within the boiler drum, when it goes too high it may result in priming. Here we are showing few impacts of impurities in the material passages, tube metal passages, due to calcium carbonate scaling in the condenser or fouling in the heaters, heat exchanger, heat transfer surfaces, or in the condensate line oxygen pitting, or high pH caustic gauging in the water oil tubes. So all these are resulting due to impurities present in the water, and that is causing this type of impact. Oxygen pitting, then internal deposits or acid attack or hydrogen embrittlement, these are quite common effects of impurities present within the boiler water, and that can damage the tube metal or flow passages and affect the performance of the system. So naturally we have to take care of water treatment accordingly. There are three basic means by which we can keep these major problems under control. First one is external treatment. treatment of water, makeup, condensate or both before it enters into the boiler or before it enters into the feedwater system to reduce or eliminate uh, contaminated contaminant chemicals like which is generating hardness or which are present as suspended solids like silica or other gases or solids. They must be removed by external treatment. Then there may be internal treatment, the treatment of the boiler feed water, boiler water, steam, condensate with corrective chemicals. Then we need to give blowdown also. This is to control the concentration of harmful chemicals in the boiler water by draining off portion of the water intermittently or continuously depending upon the requirement of the presence of total dissolved solids. The use of water in a power plant can be segmented in four major ways, and some water is required for ash handling system, some water is required for cooling water service, for domestic service water requirement, and then we require for demineralized water preparation, and we require for CW system. So naturally, depending upon the requirement of quality of water, we have different processing. Water from the raw water collected from the source is aerated, then clarified in a clarifier, then it is sent to ash handling plant and to carry the ash to the ash pond as a slurry. Then we have from clarifier chlorination is done. Then pressurized sand filter is there to separate, gravity separate the suspended solids. Then that clear water is taken into feed water tank that is used for cooling purpose, firefighting purpose and domestic use. From this tank, water is taken also for CW treatment, and the circulating water that is circulating through the condenser for collecting the heat, rejecting the heat from in the condenser. And in the condenser there if you see, we have pressurized sand filter after chlorination. That filtered water is sent to DM plant. From DM plant, water is taken to DM storage tank. From there, water is going to the makeup water tank. From there, we take to condenser or directly to boiler in the boiler feed tank. And from the boiler, we generate steam, and that steam goes to turbine, and from the turbine again it is coming to the condenser where it is getting condensed, and this condensate is passed through condensate polishing unit, then deaerator, and then again going to the boiler through feed water system. So this way the entire system is arranged so that all circuit of water supply system is appropriately processed according to the demand of the quality of water, and they are utilized in that way. Now we have also collection system of blowdowns. All the blowdowns which are contaminated that has to be collected, and these collected blowdown from neutralizing pit, CW blowdown, boiler blowdown, all are going to the effluent treatment plant. So this way we also have some arrangement to go for zero discharge mechanism or utilize the processing and primary, secondary, tertiary processing of the wastewater. Regarding pretreatment, let us try to understand the coagulation flocculation process. Coagulation is a process by which chemical which is known as coagulant neutralizes the repulsive forces between the particles which are dissolved and suspended Thereby agglomeration of particles takes place, and due to the collision with the coagulant, generally we use alum as main coagulant, and flocculation is a process of agglomeration of neutralized particle into larger and heavier flocks that leads to settling down and followed by sedimentation. So chemical applieds are known as flocculant. Different types of dry polymers, latex we use as flocculant. There may be cationic, anionic or non-ionic coagulant and flocculants. Now cationic are alum, iron salts, polymeric quaternary ammonium compounds, PACs, polyamines, polydedmac. Then we have anionic, dry polymer or latex polymer, polyacrylates, or we may have non-ionic, dry polymer. The boiler treatment program aims to control 7 broadly classified impurities like suspended solids, hardness, alkalinity, silica, total dissolved solids, TDS, organic matter and gases. And we have major 4 de-mineralization technique like distillation, electrodialysis, reverse osmosis and ion exchange. Now raw water treatment includes something like screening, pre-chlorination, sedimentation with coagulation and flocculation. Then we use the different chemicals like alum, polyelectrolytes, and filtration is also there, and post-chlorination sometimes we adopt. Now let us try to understand the membrane-based filtration process. Membrane acts as a filter that let only water flow through it and catching the suspended solids and other substances. Membranes occupy through a selective separation wall, and it can be used as an alternative for flocculation, sedimentation, purification technique, absorption, active carbon filter, ion exchanger, extraction and distillation can be avoided with this membrane filtration. The influent to the membrane feed stream, liquid passed through the membrane is called permeate, and rejected water or effluent is known as concentrate. The rate of flow of permeate is known as flux across the membrane filter. Osmosis occurs when 2 solutions of different concentrations are separated from one another by a membrane which is permeable in nature to the solvent but impermeable to solute. So solvent flows from dilute to the concentrated solution until at equilibrium the chemical potential of the solvent is equal to the both sides of the membrane. The pressure at which solvent flow is prevented is called the osmotic pressure. If the pressure is greater than the osmotic pressure that is applied to the concentrated solution, then the solvent can be forced through the membrane, leaving the dissolved substances behind. So this method of purifying water is termed as reverse osmosis. This picture is showing a layout of RO system. Now in this system, membrane elements are closely packed and the raw water is forced through it at a pressure more than the osmotic pressure, and as a result we have product water as well as the concentrate is rejected with the impurities. Now here feed water is the impure water to be treated and product water is the clear water passing through the membrane as permeate, and reject water is the water which is actually drained, and there are module combination of spiral round membrane elements and pressure vessel which are comprising this RO system. This is a typical RO plant layout. Here we find the high pressure pump, then we have different stages of modules, and first in the RO plant we have membrane package through which water is forced through the pump, and we have product water. This product water is collected in a degassing tower, and this product water is again pumped to a storage tank. So this way we arrange the RO system. Now we will try to understand the DM water preparation process by ion exchange method. In this process, ions are transferred from liquid phase to solid phase and solid phase to liquid phase by cation or anion exchange resins. This is a reversible reaction and chemical is generated for reuse, and we can regenerate the entire system according to our requirement. So the flow passage is raw water is first passed through a pressurized sand filter, then activated carbon filter, then weak acid cation, strong acid cation, then it is passed through a degasser to remove the carbonic acid, carbon dioxide, then it is passed through weak base anion, followed by strong base anion, then finally it is going to a mixed bed, and from there the clear water, DM water, is pumped to the DM storage tank. The adsorption process in the system is introduced by activated carbon, alumina and silica gel. A number of solid adsorbents diffuse on the surface of the solid adsorbents. Organic chemicals imparting color, odor, taste, heavy metals, fluorides, all are removed by this adsorption process. Large surface area accumulates more ions, and adsorption capacity depends upon the solvent-solute-solid system. Affinity and attraction are due to electrostatic force that is created by ion exchange arrangement, or physical forces, that is van der Waals forces, free movement within the system, or chemical interaction, surface attachment type. All these type of forces are impacting in the process. Activated carbon filters are first inlet stage of ion exchange process, demineralizing water treatment process. Now there we have arrangement to remove the residual turbidity, then organic molecules to control color and odor, and also we have arrangement to minimize the presence of residual acidic substances like chlorine. So we have strong acid cation, weak acid cation, strong base anion and weak base anion as a part of ion exchange process. They are acting in the principle of adsorption, which is a surface active phenomena. So activated carbon filters, they are actually removing the residual turbidity below 2 NTU, and it's they are also removing the color and odor of the organic substance present with the raw water, and residual chlorine presence may be reduced to nil level. Up to 0.5 ppm it can arrest. Vessel design, we find that they are designed as a closed vessel and with water inlet and outlet arrangement, and this vessel is provided with vent and side glass to observe the resin status. Regenerant inlet arrangement and collector plates are also present to arrest resin slippage. Weak acid cation exchange resins derive their exchange activity from a carboxylic group COOH. When operated in the hydrogen form, these resins remove cations that are associated with alkalinity, producing carbonic acid. These reactions are reversible and permit the return of the exhausted weak acid cations resins to the regeneration point, and WSC resins are not able to remove all the cations in most water supplies. There may be slight limitation, and WSC has high regeneration efficiency in comparison to strong acid cation resins, and this reduces the amount of acid required to regenerate the resin, so reducing the waste acid and minimizing the disposal problems. Now these resins are used primarily for softening and de-alkalization of high hardness, high alkalinity water, and they are always used in conjunction with strong acid cation sodium cycle polishing system, so that final results are as per control limits. In full demineralization system, the use of weak acid cation and strong acid cation resins are in combination, so to provide the economy and more efficient weak acid cation resin along with full exchange capability of strong acid cation resin gives now the strong best acid performance. Cation resins can neutralize strong bases and convert neutral salts into their corresponding acids. Now SSC resins derive their functionality from sulfonic acid groups, that is HSO3. When they are used in demineralization, strong acid cation resins remove nearly all raw materials, raw water cations, and replacing them with the hydrogen ions. Now total concentration of the strong acid in the cation effluent is called the free mineral acidity, FMA. In a typical run, the FMA content is almost stable. If cation exchange, suppose 100% efficient, then FMA from the exchanger would be equal to the theoretical mineral acidity, that is called TMA of water. And if FMA is usually slightly lower than the TMA, because sodium leakage is always there slightly from the cation exchanger. The amount of leakage depends upon the regenerant level actually, and flow rate and the proportion of sodium to the other cations in the raw water which are present. In general, the sodium leakage increases as the ratio of sodium to total cation increases. In SSC system, the exchange reaction is reversible. When its capacity is exhausted, the resin can be regenerated with the excess of mineral acid, and that way we can utilize it again in the proper functioning. The regeneration efficiency of weak acid cation resin is very high compared to the strong acid resin. Therefore, it is possible to utilize the regenerant acid strength from the strong acid unit to regenerate the weak acid unit resins, and that's why that way they are utilized for better economic arrangement of generation. Now let us try to understand the degasifier design. In demineralizing process, degasifier or degasser is used to remove the dissolved carbon dioxide. after cation exchange process. And most common degassers are the forced draft or atmospheric type arrangements, and degasser must be placed after the cation exchange column, and before cation exchange water is containing bicarbonate. So only after it the cations in water are converted into hydrogen ions, and which combine with the bicarbonate anions to produce carbonic acid. In the degasifier, the solubility of carbon dioxide in pure water is high, about greater than 30 milliequivalent per liter at 25 degrees centigrade, and at atmospheric pressure. So when water is distributed in small droplets and air is blown through it, then CO2 is due to difference in partial pressure. CO2 partial pressure is less than air. So naturally at that condition, CO2 is evaporated, broken down and getting out. However, in degassers, we can degasify only when CO2 concentration with bicarbonate concentration is at least 0.6 to 0.8 milliequivalent per liter. Otherwise, it is not effective that way. The weak base resin functionality originates in primary, secondary or tertiary amine groups. Weak base anion resins readily remove sulfuric, nitric and hydrochloric acids. So that way they are utilized just after the degasser, so that they can be effectively contribute to the purpose of ion exchange. The strong base anion resins derive their functionality from quaternary ammonium functional groups. When in the hydroxide form, SBA resins remove all commonly encountered anions. Now, their reactions are reversible and regeneration is possible with strong alkali, and therefore we use caustic soda to turn back the resins into hydroxide form. De-mineralization using strong anion resins removes silica and other dissolved solids. Effluent silica and conductivity are important parameters to monitor during a demineralization process. When silica breakthrough occurs at the end of a service run, the treated water silica level increases sharply. Often the conductivity of the water decreases momentarily, then rises rapidly. This temporary drop in conductivity is easily can be understood that during the normal run, most of the effluent conductivity is attributed to the small level of sodium hydroxide produced in the anion exchanger. When silica breakthrough occurs, the hydroxide is no longer available and the sodium from the cation exchanger is converted into sodium silicate. And this is less conductive than the sodium hydroxide. So naturally, in the process, we get this kind of implications. So anion resin exhaustion process, when it progresses, the more conductive mineral ions break through and causing a subsequent increase in the conductivity. Strong base anion exchangers are regenerated with 5% sodium hydroxide solution. In fact, the relatively high concentration of hydroxides drives the regeneration reaction. Now, to improve the removal of silica from the resin bed, the regenerant caustic is usually heated to around 50 degrees centigrade or to a temperature as per resin manufacturer's specification. Silica removal is also enhanced when resin bed is preheated before the introduction of the hot caustic. Let us now try to understand the mixed bed exchangers. Mixed bed exchanger has both cation and anion resin mixed together in a single vessel. Now when water flows through the resin bed, the ion exchange process is repeated several times, polishing the water to a very high purity. Due to increasing boiler operating pressures and manufacture of products requiring very quality water, in mixed bed exchanger regeneration, during regeneration the resin is separated into distinct cation and anion fractions. Now if you see this figure, there is service condition, mixed resin we get, then during the backwash there is separation and simultaneous regeneration is there. Something when we are draining down, it is moving down, and when we are mixing with air, again it is mixed up and giving the initial condition, and final rinse is given through the drain and the mixed bed is ready for operating again. So we find in the mixed bed exchanger regeneration, the resin is separated by backwashing with the lighter anion resin settling on top of the cation resin. Regenerant acid is introduced to the bottom of the distributor, and caustic soda is introduced through the distributors above the resin bed. The regenerant stream meet at the boundary between the cation and anion resin and discharge through a collector located at the resin interface. Following regenerant introduction and displacement rinse, air and water are used to mix the resin again, and then the resin, when it is rinsed, then the unit is ready for taking into service again. So it is important to find that we adopt different way of treatment schemes so that we can maintain desired hardness in ppm in terms of alkalinity and amount of dissolved solids and suspended solids which are not creating hardness. So this way dealkalization, base exchange, de-mineralization, reverse osmosis, all are introduced according to the quality of water requirement at various stages of use in the boiler or thermal power station for optimized performance. So far we have discussed about the various pre-treatment processes. Now we are going to discuss about the post-treatment processes or internal processes. The purpose of an internal process is to react with the feedwater hardness and prevent it from precipitating on the boiler metal as scale, to condition any suspended matter that can create hardness, sludge or iron oxide in the boiler tubular parts or metallic parts through which water stream is flowing. So to make it non-adherent to any boiler surface, and to provide anti-foam protection to allow a reasonable concentration of dissolved and suspended solids in the boiler water without foam carryover. And sidewise, the purpose is to eliminate oxygen from the water and provide enough alkalinity to prevent boiler corrosion. There are various methods of internal treatment like phosphate hydroxide, coordinated phosphate control, polyphosphate polymer based control, application of chillants, EDTA, application of organic treatment like filming amine. Hydrogen is generally used as oxygen scavenger. Phosphate or UDTA is used as a scale inhibitor. Ammonia and morpholine is used as alkalinity builder, and antifoaming and agents and sludge conditioners are used to remove the formation of deposits and sludge deposits within the boiler periphery. For pH control of boiler water, we have chemical addition arrangement downstream of the CEP discharge, and we have also online pH measurement devices before feeding to the LP feed water heaters, and we continuously maintain the pH in such a way that it is always alkaline in the system and there is no damage due to oxidation of metal. To prevent internal scaling in the boiler tubes, we adopt phosphate hydroxide method. That is, in this method we dose trisodium phosphate and caustic to maintain pH within range of 10.5 to 11.2, and calcium within the water precipitate as calcium hydroxyapatite, and it is like a non-adherent sludge and it can be drained through blowdown arrangement in the boiler drum, and magnesium reacts with the caustic to form the magnesium hydroxide that can be also removed. So this way we control the scale within the boiler tube internal tube parts. The phosphate dosing arrangement is controlled by feeding combinations of disodium phosphate with trisodium or monosodium phosphate to produce an optimum pH without the presence of free hydroxides. To successfully control the coordinated phosphate dosing program, the feed water must be extremely pure and consistent quality, and coordinated phosphate dosing does not reduce precipitation, they simply cause precipitation of less adherent calcium phosphate in the absence of caustic. Generally, a dispersant must be added to condition the deposits that would be otherwise reduce the heat transfer rate in the surface. In high pressure and high heat transfer rate boilers, the internal treatment must be so strong that there is almost no solids within the water, treated water. The potential of caustic attack or boiler metal may increase with increasing the pressure, as the free caustic alkalinity may result that if it is not minimized. So for that reason only the coordinated phosphate program is preferred. Naturally, this differs from the standard program in that that phosphate is added to provide a controlled pH range in the boiler, as we have already discussed, within the 11.2, and in the boiler water wall, as well as react with the calcium if hardness should be avoided in the boiler. Trisodium phosphate hydrolyzes to produce the hydroxide ion, and that prevents the formation of scaling. Let us try to understand the chelate programs. Now, a chelate is a molecule similar to an ion exchanger arrangement. It is low in molecular weight and soluble in water. The sodium salts of ethylene diamine tetraacetic acid EDTA or nitrile triacetic acid NTA are most commonly used chelating agents and used for internal boiler water treatment. There are addition of polymers as scale control agents that can be used to increase the effectiveness of these chelates, and this will also reduce the corrosion potential by reducing the chelate dosage below theoretical requirement, because Residual chelate in the boiler water is very problematic. Chelate can react with the oxygen under boiler water, high pressure and high temperature conditions. Though cost of this program is high, anyway, we have to remember that overfeeding of chelates and concentration mechanisms in the boiler can lead to several localized corrosion and failure. So we have to very attentively utilize this chelate application. EDTA is the most commonly used chelating agent, ethylene diamine tetraacetic acid, and this has the ability to form the stable complexes with transition metal ions in the boiler water like iron or copper. This can be segregated, and naturally this is effectively utilized for control of internal scaling. Certain complex chemicals are used for oxygen scavenging and pH boosting arrangement. Hydrogen hydrate and sodium sulfide based oxygen scavengers are most commonly used. Other oxygen scavengers are like hydroquinone and caustic soda for low pressure boilers, and for high pressure to medium pressure boilers ammonia morpholine is used. So all these elements, all these chemical compounds are effectively utilized to prevent oxygen availability within the boiler water steam circuit. As oxygen is a strong oxidizer, dissolved oxygen is the most harmful impurity in the water steam condensate circuit. The desired concentration of dissolved oxygen in the condensate or feed water is LRA, while the actual specification are 10 microgram per kg of the condensate and below 5 microgram per kg of the feed water. Dissolved oxygen control is achieved in 3 stages following the condenser air extraction system. Dissolved oxygen is removed from the condensate by the deaerator, which contains spraying arrangement and cascade trays over which the hot water is sprayed, and there is pegging steam supply through which oxygen is removed, and through a vent condenser it is disposed. The combination of heat and large surface area imparted to the water, there is very efficient stripping of dissolved gases including oxygen in the deaerator, and that reduces the total oxygen availability, dissolved gas availability below 10 microgram per kg in ppb, and nitrogen is also removed if there is some air side nitrogen contamination. This efficient stripping action reduces the consumption of hydrogen also. So deaerator improves the effectiveness of the oxygen scavenging and reducing the consumption of hydrogen. The final stage of dissolved oxygen removal is by the injection of hydrogen actually, and that is done between the deaerator and the deaerator storage tank. So to chemically control the dissolved oxygen. Now to prevent exceeding specified concentration limits of impurities, boiler water is withdrawn time to time from the boiler water steam drum as blowdown, either intermittently or continuously, and discharged to the drain. Obviously, this is apparent that substantial heat energy is lost with this blowdown, and it is a major factor to detract the thermal efficiency of the boiler. So we are always in a position to run the system in maximum most efficient condition, and therefore blowdown is always attempted to be minimized. So therefore intermittently the blowdown is allowed to maintain the concentrate to a level within the boiler water stream circuit for the particular boiler design and pressure. When this concentration level is reached, the blowdown valve is opened for a short period of time to reduce the concentration of impurities, and the boiler is then allowed to reconcentrate until the control limits are again reached. In continuous blowdown, on the other hand, actually the blowdown valve is always kept open at a fixed setting to remove water at a steady rate to drain it, maintaining a relatively constant boiler water concentration. So this way blowdown helps in maintaining the concentration of impurities within the water stream circuit. Let us sum up the internal treatments. For condensate, pH, dissolved oxygen, sodium ion, these are important parameters and they have to be maintained with appropriate arrangement like ammonia dosing, morpholin dosing, and their desired condition is ALARA, that means as low as reasonably achievable. Similarly, feed water, dissolved oxygen, total iron, total copper, hydrogen, these are important control parameters. Then boiler water, cation conductivity, pH, and chloride, sodium, silica, sulfate, their concentration. These are all has to be maintained as per desired condition. Again it is ALARA, that means as low as reasonably achievable. So this way we have to control the concentration of impurities as per the requirement of the system and get the best output of water quality with appropriate pH, TDS, suspended solid and dissolved solids, dissolved oxygen. So all these things has to be maintained. For high pressure boilers where we have condensate makeup that is added in the hot oil more than 90%, the treatment process is phosphate plus hydrogen hydrate plus morpholin. And for low pressure boilers or power boilers, comparatively process boilers or power boilers, where we have fresh makeup up to more than 50% and we are using DM water, there we use filming amine as the process to treat the water. So there are 3-stage arrangement. Trisodium phosphate is dosed at deaerator, boiler drum. Then hydrogen is dosed in the deaerator discharge, and we have ammonia dosing, morpholin dosing in the deaerator tank. So this way, in a combined arrangement, we try to control. In this slide, we find the boiler water parameters and according to pressure, how the control parameters are reflected and how the control mechanism is adopted in different boilers according to their operating pressure and temperature conditions. So we utilize the recommendation of original equipment manufacturers in terms of internal treatment. So in that way we maintain the alkalinity, we maintain the concentration of silica, sodium and TDS, conductivity, hardness, pH. So these are monitored accordingly as per OEM reference, as per previous experience to get the best possible water quality. So we can go for any type of internal treatment, but we must have to ensure that all parameters related to impurities in the feed water, boiler water, steam and condensate, and they are within the limit, and that has to be ensured with no scaling, no corrosion, no carryover within the system. In thermal power station, a large amount of wastewater is generated which is sent to the effluent treatment plant, and this effluent treatment is done in 3 phases. There is primary treatment, secondary treatment and tertiary treatment. The primary treatment in the effluent treatment process is mechanical process for influent sewage. It is done by screening. It is first the wastewater is screened so that we can retain all the coarse solids found in the wastewater, and according to the method of cleaning, screen may be hand cleaned or mechanically cleaned. Mostly we have arrangement to collect the whatever is large objects coming with this wastewater above quarter-inch or more size, that has to be segregated. Sometime a motorized screen is also utilized for segregation of whatever coarse solid is coming with the effluent. Now there is some physical treatment also, that is sedimentation. Sedimentation is separation from water by gravity settling of suspended particles which are heavy than the water. Sedimentation is used for separation of particulate matter in the primary settling basin, separation of flock in the activated sludge settling machine, separation of chemical flock when chemical coagulation process is used, and it is also used for solid concentration in sludge thickeners. Sedimentation basins are constructed according to requirement of size and shape. Circular or rectangular tanks are available for sedimentation. It comprises the 4 zones: inlet zone, settling zone, sludge zone and outlet zone. Inlet zone is distribute uniformly the incoming suspended and dispersed particle over the cross section of the tank. Settling zone is to settle the particles at the same rate. Now outlet zone is to remove the clarified liquid which has to be collected and dispersed, and solid collects in the sludge zone has to be periodically removed from the bottom of the tank. So this way sedimentation arrangement is provided. Now secondary treatment is based on biological treatment process. It removes dissolved colloidal and organic matter from the wastewater. Microorganisms are converted into non-settlable solids to settleable solids, like all the bacteria and other arrangements. There are 3 types approaches to conduct this secondary treatment: fixed film systems, suspended film systems and lagoon system. All the 3 systems are available and adopted according to the requirement. Trickling filters are one of the secondary treatment mechanism. Organic material present in the wastewater is metabolized by this biomass, and biological slime grows in the thickness of the organic matter. So there is a constitutionally liquid matter whatever is coming, so that is abstracting the solid waste, and wastewater is synthesized into new cellular material. Liquid then washed with slime of the medium and new slime layer is generated. So collected liquid is passed to a settling tank used for solid liquid separation. So this way they are continuously working. There are rotating biological contractor also. So they are actually consisting a series of closely spaced plastic circular discs. These discs are submerged in wastewater and rotated slowly, and biological growth become attached to the surfaces of the disc and form a slime layer over the entire wetted surface. The rotation of the disc contacts the biomass in the wastewater and then the atmosphere for the absorption of oxygen is there. So oxygenation is also taking place. So biomass uses this oxygen and organic matter for food, thereby reducing the BOD, biological oxygen demand of the wastewater, and thereby getting better low biological load clean water. So this way they are utilized as secondary treatment process. In the suspended film system like activated slush system, there is continuous stirring and suspended microorganisms in the wastewater which absorb the organic matter and nutrients from the wastewater, and naturally they settle as sludge, and after settling the remaining water is taken out from the system. The lagoon system consists of in-ground earthen basins in which the wastewater is detained for a specific time and then discharged. They take advantage of natural aeration and microorganisms in the wastewater to remove the sewage. So naturally this way the settling of the sludge is taking place and clear water is moving from the top. Tertiary treatment or disinfection is done for the purpose of destructing the harmful pathogenic microorganisms which are disease causing germs. It is done through chlorination, ozone, ultraviolet light or hydrogen peroxide. Mostly chlorination and UV arrangement is preferred for the purpose of use. When the effluent treatment is done, the clarified effluent is taken back to the raw water stream after a final carbon filtration and chlorination, and the sludge, which is very nutrient rich, which can be used as a fertilizer in the land for agricultural purpose, or may be used as a good fuel for incinerated arrangement, or it may be used as a compost. So that's the end of the topic on power station water treatment and wastewater management. If you have any queries, please feel free to contact me through mail, and I will definitely oblige to answer your queries. Happy learning, all the best. Thanks.